Assalamualaikum and good day to Doctor. So today I'll be presenting with my group our topic, which is underground hydrogen storage in depleted reservoirs. So we'll be focusing on the feasibility and challenges of repurposing gas fields for hydrogen storage, and we are from Group B. So this is our team members. So it consisting of me, myself, Muhammad Masjid bin Hassan, and Shauki, Najmuddin Arshad, Cik Wanawi Amira, Hakimi, and also Haikal.
So good morning. So I will be presenting to you the introduction of UHS, which is underground hydrogen storage. So what is UHS? It is a method of storing large volume of hydrogen gas deep below the Earth's surface. So instead of building expensive tanks above the ground, we use natural geological formation, which we targeted specifically in depleted oil and gas reservoir, aquifers and salt cavern. So basically, normally we use depleted reservoir because it has been proven that it can hold gases safely for millions of years, and we can reuse the existing well and pipeline, saving the time and cost. So how does it work? We inject the hydrogen gas into the rock through the wells, pushing out any leftovers water or gas. So and then a thick impermeable layer of rock called the cap rock acts as a lid which seal the hydrogen in place, just like a natural storage tank. So we're moving on to the relevance to gas engineering. So how does it relate from gas engineering to UHS? So reservoir and well, we uses reservoir and well expertise, where the gas engineer apply their expertise in reservoir simulation, well integrity and fluid dynamics to optimize the hydrogen injection and withdrawal cycle. So does it have a role in energy transition? It does. Enables large-scale hydrogen storage for industrial use, power generation and fuel cells. So as we can see from the picture, it is showing that the hydrogen generates power for the industry use, and also we can inject the excess energy over to store them in the UHS storage. And then it also supports decarbonization by balancing the renewable energy fluctuation, and then it bridges natural gas expertise to hydrogen economic demands. And for the future outlook, UHS could become a cornerstone of hydrogen supply chains, and also gas engineer will drive innovation in safe, efficient storage solution.
Alright, so next we'll move on to the key concepts and principles. So first of all, I would just like to explain there's three common types of underground reserve. The first one is salt caverns, second one is aquifers, and the third one is the case that we're studying, which is for depleted reservoirs. So I'd just like to highlight four important key parameters that we need to look for in reservoir before we can really decide if it is suitable for hydrogen underground placement. So for the first one is porosity. So of course we want to know if the porosity is suitable or significant enough for us to store a good amount of hydrogen inside. Next one is permeability. So we want to make sure that we are able to control what we are already injected, especially the hydrogen itself, because we need a reservoir that can flow the hydrogen in a very good possible way. So that is why we need a good permeability. And the third one is cap rock integrity. So of course, as we know, we need a good cap rock for us to store the hydrogen itself within the reservoir, and the cap rock itself has to be impermeable. And the last one is residual gas saturation. So this is quite special because usually depleted reservoirs have methane content, which can combine with hydrogen and forms byproducts which could disturb the overall flow of the hydrogen itself. So we need to monitor and make sure that we choose a good one for the residual gas saturation. So these are the key concepts that we need to look for in depleted reservoir hydrogen placement. Right, so now I'll just move on to the principles. So why we choose depleted reservoirs as one of the candidates for us to store hydrogen. So there's five important principles. So the first one is abundant capacity. It is proven that the reservoir can hold a huge amount of oil or gas before, so it is suitable for us to like store hydrogen itself. And next one, it is proven to have a geologic stability, so it is important for us to like secure the hydrogen that we already plant, and to also make sure that it can sustain for a long term. Next is scalability, which will allow us to for scalable storage solutions. And number 4 is environmental benefits. So of course, we want to store hydrogen in the most efficient ways and in the way that we don't want to hurt or affect the environmental aspects in a bad way. And the last one is reuse of infrastructure. So of course, this is directly affecting to the cost that we could cut in the long term, because we don't have to like plant and place a new infrastructure for us to process the whole thing back, instead of just using the old infrastructure. So that is the 5 key reasons and principles why we choose Deepwater Reservoir to store hydrogen underground.
Hello everyone, today I will talk about the technical and engineering challenges of storing hydrogen underground in oil gas reservoir. So the first one is reservoir compatibility. First, we must check if the reservoir is suitable. So as you know, hydrogen is the smallest and lightest molecule, so it is very small gas. So it can diffuse through rock formation and well materials easily. So it is not like methane, and it can move through rocks and escape much more easily. So the next is seal quality may be insufficient for long-term hydrogen containment, which means the oil gas field may not have a strong enough seal to keep hydrogen inside. Geomechanical assessment and cap rock recharacterization are essential. So it's stated that we must study the rock and cap rock carefully before using the reservoir. So number 2 is hydrogen-induced embrittlement. Next, we have a problem that are called embrittlement. Hydrogen can damage steel and metal parts. It can cause steel and alloy component to become brittle. So tools such as pipes and valves used for natural gas may become brittle and break with hydrogen because it is not originally designed for hydrogen. So it will increase risk of material failure and also gas leakage. So how to solve this? We need to solve this by using stronger materials or special coatings that can handle hydrogen. The third one is microbial activity. Hydrogen can also feed bacteria underground, which means that it may stimulate the microbial growth underground, which is inside the reservoir. So some bacteria such as sulfate reducing bacteria can produce H2S gas, which is this gas is toxic and it will cause corrosion to our tools, and it will risk of souring the gas and damaging the infrastructure, and this is bad for both safety and the equipment. But we can control this by using chemical to kill the bacteria, such as biocide treatment protocols, and by monitoring them. Then we move to number 4, which is cushion gas. Cushion gas is a minimum amount of volume of gas which is non-recoverable and that are required to maintain the pressure inside the reservoir. So in hydrogen storage, we cannot remove all the hydrogen that we store. We need to leave some gas in the reservoir to keep the pressure become stable. But hydrogen is very expensive and it is difficult to recover, such I said. So we may use inert gas such as nitrogen, or we leave just small part of hydrogen to save some cost. The next one is injection and withdrawal design. Hydrogen has a low viscosity and has a high diffusivity. So hydrogen moves faster than another natural gas, and it can leak out more easily during injection and also withdrawal. And it is also hard to control the way it flows underground, which is inside our reservoir. So we need a good advanced modeling such as simulation models and flow control technologies such as special valves to manage the flow much more safely. Then we go to the last one, which is monitoring and safety. Hydrogen is a colorless, odorless, and highly flammable. So existing gas monitoring system right now cannot detect low concentration of hydrogen leaks. So this is make us hard to detect some of the leaks. So we must use high sensitive detectors and monitor the pressure and temperature all the time, because safety is very important for hydrogen storage. So, in summary, storing hydrogen underground is possible, but we must solve many challenges to ensure this process has a good safety and has an optimum effectiveness.
Hi everyone, today I'll be presenting key industry practices and research trends in the emerging field of underground hydrogen storage, specifically in depleted gas reservoir, a solution critical to supporting future clean energy systems. So number 1, site reuse and screening. Energy companies are repurposing depleted natural gas field because these sites already have proven seal integrity, known geology and existing infrastructure. This significantly reduces development costs and improves safety during hydrogen storage process. Companies like Equinor and Eni are using advanced reservoir models to screen and evaluate the site for hydrogen compatibility. Number 2 is pilot project. Full-scale pilot projects are actively testing hydrogen injections and withdrawal. Great example is RAG Austria underground sun storage, which successfully demonstrated that over 80% of injected hydrogen could be recovered from porous rock formations with minimal loss. These pilots help validate design assumptions and operational safety. Next is gas cushioning. Another key industry practices is the use of cushion gas, usually nitrogen or residual methane, which is injected before hydrogen. This helps maintain reservoir pressure, ensure stable flow, and minimize mixing between hydrogen and formation fluids. However, some studies have shown that cushion gas can be lost during production, so optimizing this balance remains an active area of development. Okay, next is the research trend. Number 1 is hydrogen flow and trapping modeling. On the research side, scientists are simulating hydrogen flow in porous media. Unlike methane, hydrogen has higher diffusivity and lower viscosity, which affects how it moves and gets trapped underground. Models are being developed to predict residual trapping, leakage risk, and recovery efficiency under different geological conditions. Number 2 is microbial activity studies. Ongoing research is investigating how microorganisms in the subsurface may consume hydrogen and generate harmful gas like hydrogen sulfide. Studies from Italian gas fields have shown this is a real concern. Researchers are working on mitigation strategies, including biocides and reservoir conditioning to preserve hydrogen quality. Number 3 is geomechanical simulations. Researchers are analyzing the mechanical behavior of reservoirs under cyclic injection and withdrawal. Hydrogen injection can alter pressure and stress regimes, possibly leading to capped rock fatigue or fault reactivation. However, early findings suggest hydrogen causes less stress than CO2, which is promising for long-term operation.
Okay, let's move on to case study and real world application. So the first project is UHS pilot project, Highstock from Netherlands, located in salt cavern facility but exploring integration with depletion field nearby. The goal is to develop large-scale seasonal storage for green hydrogen from electrolysis, and hydrogen produced from excess wind and solar energy is stored and reinjected based on demand cycle. The second one is UK project U21 Northern Gas Network. The aim is to convert the UK gas grid to hydrogen. The Teesside and Yorkshire region include depleted gas field being evaluated for UHS. Geological survey show promise for storing hydrogen in Permian Basin Formation. The next one is Germany H2 storage high performer. This project is focused on using North German gas field for underground H2 storage. Early geology modeling show safe containment, but conversion and microbial reactivity study are ongoing. The last one is United States low hydrogen shot initiative. So this project include a feasibility study for underground hydrogen storage in depleted oil field in Texas and California. Research found to test hydrogen migration, leakage potential, and material compatibility in legacy well.
For the conclusion, first strategy is as natural geological formation like depleted reservoir, earth, aquifer, and salt that provide large volume of hydrogen storage at lower cost compared to the surface infrastructure. So in their subsurface, location will offer the thermal and physical protection environmental factor that reducing the explosion risk and enhancing overall the storage safety. So for the second, we have the hydrogen storage depend on rock and fluid properties, which is the success of the underground hydrogen. Storage depends on the rock ability to hold and move gas, which can change the under pressure. So it also depends on how the hydrogen behave as a fluid, especially like in properties of density, viscosity, solubility, and diffusivity control hydrogen behavior. So in porous media, it also depends on how hydrogen behave as a fluid. So the last but not least, we have innovation. Like in the research study around the pilot projects, especially we helping prove that underground hydrogen storage can work safely and effectively. So for example, we have the well retrofitting, which focus on oil and gas well that being upgraded to handle the hydrogen without leaks and damage. So next example, like monitoring technology, like the new development of new tools that been developed to track the pressure, temperature, and also possible to check the leaking in real time. So that's all from our group.
Alright, so these are the list of references that we all use to make sure that we get a high quality information from the research itself. Alright, so that is all from us, Group B. Thank you.